Good evening, my dear JEE 2026 warriors. The class 12 syllabus is on full fire, and we are on to the last session of our electrostatics Gauss law. And today we're going to see everything about conductors, dielectrics. Dielectrics is going to be in the next part, which is the capacitors. So pay attention closely. And of course, the shell and the plate problems. So everything today in this amazing class for your class 12. So usually I know the class 12th portions are being conducted at 8 o'clock, but since Diksha ma'am had some, other, what do you say, commitments. So that's why we had to exchange the classes just for today. So let's begin with the class, and I hope you guys are all ready with full firepower for the final session. Everybody, I hope I'm audible and visible clearly. Yes, your Captain Shreyas is live, and mention your name, say hello, everything, guys. And last lecture we had completed, let me just show it to you over here. Vernier caliper was your 11th standard topic. We just did electrostatic flux and Gauss's law and its applications, all the derivations we have done. The PDF has been shared over here. You can open the PDF at any point of time, right? And I'm so glad Sivarama, TGZ, I'm so glad micro courses HC Verma and Erodo available on the Vedantu website. But when I tried to look into it, unable to find any of them have been discontinued. Yes, it's a very old course. I mean, not very old, but like 2 years. So I think it is not there on the website anymore. But if there is a particular demand for those HC Verma courses and Erodo courses, let me make it available for all of you. Okay, maybe in the Sigma batch or something, and maybe I can do it. Let me see if it can be done. All right, cool. So let's begin with the class, and yes, make sure you're solving the homework and downloading the PDFs on a regular basis. Hi Rama, hi Sai. Good evening, my dear warriors. So let's start with the properties of conductors, and also take a moment to appreciate our toppers this year in JEE Advanced 2025. 1 out of 3 Vedantu students clearing JEE Advanced, a big feat in itself, and scoring all India rank 15, clearing Olympiads, and topping the state, everything, guys, from your seniors. Why I show this is because this is what I expect of you next year, and majority of them were online students. So don't even think in your head that, oh, if I'm watching YouTube or online, can I crack it or not? Well, you can get into IIT. These students have proved it exactly, laid an example. So now you have nothing to fear. Just idolize them, and in fact challenge them by scoring better than them next year. That's when I would be proud to see you guys, in this leaderboard, right? Okay. So conductors, like we have talked about the different types of solids based on how they conduct electricity or not. So conductors are the ones which conduct electricity when you connect a battery or apply a voltage across it. So they have, basically they have electrons. The electrons can be mobilized. The electrons can be mobilized. The electrons can be mobilized easily by applying potential difference, to conduct to conduct to conduct electricity to conduct electricity. Copper, metals, aluminum, iron, gold, silver, even graphite, and even saline water, or even normal water to some extent, are categorized as conductors. Rubber, wood, plastic, etc., non-conductors. There is also a separate chapter for semiconductors, which is the last part of 12th standard. We'll be talking about it later on. Right? Hi, education world. Good evening, my dear warriors. Right. Now, when you talk in terms of electrostatics perspective, what are those special unique characteristics that these conductors possess in terms of electrostatics? Now, please remember the chapter that we are studying over here right now is the chapter of electrostatics. Electrostatics. So, we are talking about electrostatics. electrostatics. So when we are talking about electrostatics, electro is a general representation of charges, and statics means they are at rest. They are basically at rest. So even though they can mobilize the electrons, they can conduct electricity. In this particular chapter, the charges themselves are not moving as such, or you are seeing equilibrium conditions. So the charges are at rest, or I would say they are at equilibrium conditions. They have attained equilibrium conditions. So they are not moving as such. In the chapter of current electricity, it is electrodynamics, and dynamics or kinematics or kinetics means it is in motion. It is, it has moving, it has started moving. So here the charges have attained a sense of fulfillment. They are in equilibrium. So in that perspective, we'll be analyzing the conductors. So first of all, the most important property, being inside a conductor, the electric field is zero. One of the most important property. So if you take a conductor, like this, or even a conductor with some cavity. Cavity means there is some hole, some vacuum kind of thing, something which is empty. Doesn't matter. No matter where you go, everywhere here, everywhere the electric field is zero. So at all these points, all the points marked red, as you can see, the electric field is zero. So in fact, chunk of that solid, that whole chunk of that solid, the electric field is going to be zero in the solid part of the conductor, in the solid part of that particular conductor, everywhere. And there is a reason for it. And the reason for that, I can argue by something called as a method of proof by contradiction. We can prove it by contradicting it. Proof by contradiction. Proof by contradiction. What is this proof by contradiction? Let's assume, let's assume, let's assume electric field in the solid part of the conductor is not zero. So if the electric field inside the solid part is not zero, then what will happen is that conductor which is there, okay, it has some electric field, it has some electric field inside that solid part. And remember, a conductor has a lot of free charges. It has a lot of free charges, basically electrons. So definitely there will be electrons over here. If there is a charge and there is a field, immediately there will be a force on it. Immediately, therefore, there will be a force on that charge. There will be a force on those free charges, and it will definitely not be zero. Why am I showing in the opposite direction? Because electrons have negative charge, so force will be opposite to the field. What will this force do? This force will start moving the electrons, moving the charges. It will start moving the charges. Now this is exactly against my chapter's heading, electrostatics. The charges must be at rest. They should have attained a sense of fulfillment. They should be satisfied. They should be at equilibrium. How can we have the charges in motion? So hence comes the contradiction that but the charges must be at rest. The charges must be at rest because it's electrostatics. We are talking about static situations, not dynamic situations. So our assumption is wrong. Therefore, assumption is wrong. Therefore, assumption is wrong. And once our assumption is wrong, that means whatever is given over here is absolutely correct. Understood this proof by contradiction method? You can use it in daily life also. Your teacher says that you have stolen somebody's pencil or pen. You prove it otherwise. Okay. So, you prove it otherwise. and you are arguing with the teacher, no ma'am, I have not done it, I have not done it. So you assume the teacher has said whatever has said has been correct, and then you find some contradictory thing. Oh, you have stolen the pen at 12 o'clock, and then you figure out, oh wait a minute, at 12 o'clock I was not even there in the classroom. Hence it's proved that if you could not be there at the same time when the pen was stolen, that means you were not stolen the pen. Hence whatever assumption was there is wrong. So this is the method of proof by contradiction. Is this absolutely clear, everyone? So inside the solid chunk part of the conductor, everywhere the field is going to be 0. Okay. Next important thing. At the surface of the conductor, the electric field, see this is outside now. Inside the conductor, the field is 0. But on the outside part, the field from the surface is always perpendicular at every single point. So say for example, this is your conductor. This is your conductor. Okay. It says that if you have some electric field like this, or maybe like this, maybe like this, like this, like this, like this, whatever. These electric fields are always going to be perpendicular to the surface. Yes, these are basically your electric field lines. These electric field lines, afterwards they might bend, that's okay. But at any given point on the surface, if you draw the tangent, it's always going to be perpendicular to the surface. It's always going to be perpendicular to the surface of the conductor. Again, you can use the method of contradiction. So if you use proof by contradiction, again we'll be able to prove this very easily. It's a valid way of proving many things in physics, mathematics, anywhere. So let's assume that this is the conductor surface. Okay, let's assume that this is the conductor surface, and let's say that our electric field is not perpendicular. So our electric field is making some angle. So by proof by contradiction, just like over here, so let's assume that electric field makes an angle with the surface. So now the electric field will have two components. One component will be parallel to the surface like this, and there will be other component which will be perpendicular to the surface. Now, once we have two components, look at the parallel component. Look at the parallel component of the field. The E parallel component, because it is making an angle, applies some kind of force on the charges. Remember, there are electrons over here. Electrons will experience a force in the exact opposite direction like this. Will applies some force on the charge carriers, or the free charges. The moment it applies force, what will happen? Therefore, the charges will be in motion. Therefore, the charges will be set in motion. But how is this allowed? Because electrostatics, we are dealing with static situations, hence our assumption is wrong. So the charges will be set in motion, which is not possible, which should not happen. Hence our assumption is wrong. That's it. Hence our assumption is incorrect or wrong. Is that clear? How we have proved it by contradiction? So there cannot be any parallel component, only perpendicular component can be there. And even if the perpendicular component is there, remember, it cannot throw those charges, beyond a point. I mean, that is the end limit. After that, it's a completely vacuum space, non-conducting space. So the charges can't really leak out from there. So that perpendicular component will just push it till the extremities or the boundary. It can't throw it outside the conductor. Is this clear, everyone? Till this point? Okay, perfect. Next important property. The interior of a conductor can have no excess charge in any static situation. Very interesting property. Observe. So imagine this is our conductor. Okay. It could also come with some cavity. It really doesn't matter. Assume that there is no other charge, but the conductor itself is being given some charge. Then you will always notice that the charges on the conductor will lie on the outermost surface only. Yes, they will lie on the outermost surface only, like this. The charges will lie on the outermost surface. Very, very important. So, this is basically the outermost surface of that conductor. That's where those charges are going to lie. And you can prove it by Gauss's law. You can very easily prove it by Gauss's law. How? Imagine that if you take a conductor and if you choose any Gaussian surface, what is this? This is basically our Gaussian surface. Any Gaussian surface in the solid part of the conductor, in the solid part of the conductor, the cyclic integral E vector dot dA vector will be the charge inside by epsilon naught. Do not forget that our first property itself was the electric field in the solid part of the conductor anywhere is 0. So 100% this particular thing, this electric field which you see, this itself is a 0. So therefore LHS is 0. Therefore the charge inside must be 0. So this part has no charge at all. So there should be no charge over here. There cannot be any charge here. The inside charge should be basically 0. So whatever charge is there should be there on the outermost periphery. Therefore, I can argue, what is the maximum Gaussian surface that I can take? The worst Gaussian surface I can take is this one along the surface like this. So that is the last Gaussian surface I can take. So inside that also there will be no charge. So the charge will be just on the surface. Inside there will be nothing, just outside. So the charges are trying to run away from each other. And it kind of makes sense. Like, look at these charges. They are all positive or negative. They hate each other. Like charges repel each other. So they tend to move away from each other. And as a process, as an outcome, they end up coming on the boundary of the surface of the conductor. It's like you have 20-30 people who hate each other in a class. They will tend to sit away from each other, and probably they are sitting near the walls. They are not at the center accumulating. Hence, that is the reason why therefore the charges repel and stay on the surface in static condition. Okay, I hope this is absolutely clear in everybody's head. I'm explaining each and every point. Nobody will tell you guys all these things. I'm telling you. Hi Vasuki, welcome. Thank you for marking the attendance. When will you start current electricity? Dharwant, see, 2 lectures, I think we will have 2 or max. Yeah, 2 lectures on capacitors. So next week we'll complete capacitors. After that, we'll start with, your current electricity. And current electricity will be done in July. And then we can start with magnetism immediately. Right? Everybody excited to complete the full syllabus on time, in rhythm, in momentum. Please get accustomed to these classes, attend the classes regularly, don't miss. Because see, this is your Captain Shreyas Sir's promise over here, and you are getting the best quality content. After this, there is no doubt which should stay in your head in physics. There is no reason why you cannot get 99.9 percentile and above. Got it? Yeah? Great. Yes, the Gaussian surface is always an imaginary surface. So you can imagine whatever surface. So if you worst come worst, imagine the entire surface of the conductor to be Gaussian. Nothing will stay inside. So everything should stay on the surface, not inside. So the worst possible scenario also, you will see it will be on the outer periphery. Nothing can stay on the surface of the cavity. Remember, this is a cavity. Nothing is there on the cavity. Okay. Unless there is a charge inside, which will come to it later on. For now, there is no charge at all. All right. Now this is actually, I should have put this before only, fourth property. Electric potential is constant throughout the volume of the conductor and has the same value as on its surface. This is so simple, guys, to understand. Because imagine if I have a conductor, let's say like this, some random conductor, chumma I'm taking. Then because everywhere inside the field is 0. Inside the field is 0. But if you go outside, well, the field is there. Well, the field is there, right? That's how it is. Something like that, maybe. So outside there is field 100%, but inside there is no field. The moment field is 0, do not forget electric field is nothing but negative dV by dr. So if this is 0, what does it tell you about this? This whole quantity is also 0. Therefore, whose derivative is 0? Constant. So the velocity, sorry, not velocity, potential inside is going to be a constant. This is a simple proof for that. The most easiest way to prove it. Electric field is going to be 0 everywhere. We have proved that in the first one. So derivative will be 0. That means the constant's derivative has to be 0. So potential is constant everywhere. So the entire surface, including inside, is equipotential. So this whole thing is basically equipotential. So I can mark this entire thing. Yes, this entire thing over here will be at constant voltage. Voltage will be constant. Voltage will be constant throughout. But the moment you go outside, voltage will not be constant. In fact, you will start seeing equipotential lines like this. These will be the equipotential lines outside. Yeah, this is how it will look like. They will be circling or enveloping, the solid surface, almost like the same shape as the solid. But as you move away, the shape gets diluted. You can hardly make out, and it will slowly start becoming circular in nature. So these are equipotential lines outside. Equipotential surfaces outside the conductor. Outside the conductor. Outside the conductor. If you ask me the electric field lines, they will be always perpendicular everywhere. So maybe they will go like this, maybe like this. Yeah. Something like this. Okay. So this is how the field lines will look like. And those will be the equipotential lines. So this is how, the fields and the equipotential surfaces behave for a conductor. Is this absolutely clear, my dear warriors? Done, dusted. Shall we go ahead? Okay. Right. Hello, Caps. Big fan for your Chuma. Oh, thank you so much, Vijaya. Hi, Spidey Throne. Rama, please solve advanced PYQs for time management. Oh, yes. I'm planning to solve some advanced questions specifically, or some good level questions in the near future once a decent chunk of the syllabus is done. Okay. This time I'm going to create a very different version on YouTube. Okay. We are no longer going to aim for 90 percentile. We are going to aim for all India rank below 1000. Below 1000. not just in J Advance, but in every single exam, be it Olympiads, be it IIT, be it NEST, be it BITSAT, be it any other exam, guys. We will try to come into the top creamy layer. We are going to push ourselves to the extremes with challenging questions. But let's complete a decent chunk of the syllabus so that we have enough time. And it all depends on your support, your show of strength, how much you are talking about Vedantu J English, how much you are showing your regularity. If that sincerity is seen, then I can do it. But if it is not seen, then okay, right. Okay, moving on. Next one, electric field at the surface of a charged conductor. This is also very important. There are two main things related to that. And one thing is observe, if you have a conductor which looks something like this, you will see the part where it is sharp, there you will have many electric field lines coming out of it. But the part which is blunt, well, maybe not so much. Maybe some few electric field lines. That's it. And that also depends on the charge density over here. There will be more charges over here. There will be more charges over here versus very few charges over here. So what this tells you is there is if it's a very sharp part of the conductor versus this is a blunt means it's not sharp, it's opposite of sharpness. There you will see a strong field at the sharp part, you will see a strong field at the sharp part, but here you will see a very weak field. In fact, there is a direct relationship for this, and the relationship is as follows. It is nothing but the charge density. The charge density is, this is the surface charge density. The surface charge density is inversely proportional to the radius of curvature, is inversely proportional to the radius of curvature. As you can see over here, my dear warriors, that this is the radius of curvature versus this radius of curvature, right? Over here, the radius of curvature is more, here it is less. So when R increases, as you can see at the blunt surface, the surface charge density becomes less. But when R reduces, small curvature, sharp means very fast turn, very quickly it will turn. It's a sharp turn. So radius will be less. There the field and the density of the charges will also be higher. Is this clear, my dear students? Yep, perfecto. Now, this is also the reason why, imagine there is a Pandu over here or maybe Champa over here. So beautiful Champa out here is, so this is beautiful Champa over here. She has very, very nice hair. She has very, very nice hair over here. Okay. And this Champa is enjoying and dancing in the monsoon. Okay. In the rains. But then what happens is Champa's hair, suddenly it begins to stand like this. So Champa's hair, it begins to stand like this. And Champa is like, wow, I can make a new reel out of it. I can go viral. I will get 1 million views. Champa's hair starts, standing like this. This situation, if it occurs to you in real life, please run. Yes, please run as soon as possible, because a lightning is about just few seconds away to strike you. So run for your life. SOS. Save your souls. Okay. So why is that? As you can see, the clouds above, there is lot of charge built over it. And lightning is about to strike. So these charges are trying to find a path. The charges are trying to find a path to the ground. So they look for anything which is a conductor. That's why tall buildings, towers, sharp objects are favorable for them, because those sharp objects, the fields can become very strong at those sharp edges. The fields can become very, very strong at those sharp edges. But the moment the edges are blunt, like the earth, here the field will be not so strong. Here it will be very, very weak. Versus here, it will be very, very strong because it is a sharp edge, and here is a conductor. Yes, human body is a conductor. So here edge is also a conductor. So the fields start accumulating on the edges, and when the fields become strong, then the electron discharge can happen very, very easily. So the charge can flow, the flow of charge can happen very fast. It can happen easily. The flow of charge can happen easily. That's why you will see on tall buildings, there are usually these lightning conductors, which are sharp objects. That is deliberate. That is not, oh, why sir, sharp lightning will strike. That is what you want. See, sometimes you don't want the lightning to strike you, so you sacrifice someone, so or something. So in this case, it is that lightning rod on the top of a building. So that lightning conductor has a very sharp edge. So when the charges build up in the sky, in the clouds, and they are looking for an escape route towards the earth, then you will see that the moment those sharp edges are there, electric field will be strong, and the electrons will find an easy passage via that strong electric fields. Stronger the fields, there the forces are higher, the passage or the mobilization of the charges is easier. So that's the reason for it. Is this absolutely clear, my dear warriors? Yeah. Where is Pandu? Pandu is safely, probably watching the reel of Champa. Yeah, maybe he's liking the reel of Champa as of now. Right. Now, another important thing is over here. Say for example, if you if you if you take this particular conductor, any conductor, and we all know that the electric field is always going to be perpendicular and it will be outside. Electric field is always outside the surface of the conductor. Electric field inside is going to be 0. Let's say if you take the surface of the conductor, the charges are distributed like this. And we know something like sigma, which is the charge per unit area, whose unit happens to be coulomb per meter square. Okay, charge per unit area. Then you can calculate how much this electric field is just outside the conductor. So the electric field just on the surface, outside the conductor, is simply sigma by epsilon naught. But we already know the electric field inside the conductor, that is always going to be 0. This proof you can do it using Gauss's law, just like we did it for the plates part. Just like we did it for plates, where it was sigma by 2 epsilon. Here it is sigma by epsilon. Sir, I get confused, sir, when to use by epsilon or when to use by 2 epsilon. I'll tell you an easy way to remember. Okay, after this, you will never be confused. If you have a sheet, then the field will go two ways. Here also, here also. When sheet, plate, something like that is mentioned, the charge will be on the plate or the sheet, and the field will go both ways. So in that case, when it is going two sides, then it will be sigma by 2 epsilon. Two sides, so 2. Here the field is going only on one side. So sigma by 1 epsilon. Now is it easy for you to remember? So going two sides by 2 epsilon, going only one side, sigma by 1 epsilon. Is that simple now to remember, guys? Quickly smash the like button in case you have forgotten to do so. Many people do forget. Yeah. All right. Okay. Very good. Excellent. All right. Got it? Yes, Vijay Lakshmi. How can current travel in air? That is called as dielectric breakdown. Okay, we'll just probably talk about it for a moment over here. So, lot of students have this question: can uh, electricity can electricity flow in a non-conductor, in a non-conductor like air? Example. The answer to that is yes. Even air, even air can allow the charges to flow, but there is a big if over here, and the reason and that condition is only at very high voltage differences, voltage difference, or field, very high, very high, very high voltage differences, or very high, or I can say strong, or very strong fields, very strong fields. Not for small fields, not for low fields, it is not possible. For very strong fields, the force becomes so high that even the air molecules can, even the air example can become conducting. Okay, vacuum can never become a conducting material because vacuum has no electrons only to spare, but air, hydrogen, nitrogen, oxygen, they have electrons. Those electrons don't come out so easily. So you need a very strong voltage or electric field. So the field at which this happens, so or rather when this happens, it is called, this phenomena is called as electrical breakdown. It is called as the electric breakdown of the medium, breakdown of the medium, electric breakdown of the medium. And the electric field at which it happens, the electric field at which it happens, you can call it as the breakdown field. You can also call it as the breakdown field, breakdown field strength of the medium, breakdown field strength of the medium. Okay, whatever that field is, you can call it as the breakdown field strength, or sometimes called as the dielectric strength, dielectric dielectric strength of the medium, dielectric strength of the medium. Okay, sometimes. Is that clear, guys? Everyone with me on this? That is the strength till which it can hold on to stop the electricity, but once that field is beyond that limit, then conduction of electricity happens, and you will see that you have broken the barrier and you have broken the strength of that material, and conduction begins. All right. Vijaya, highly recommend you join the Sigma batch apart from the YouTube series, because a regularity of test series will come, a punctuality will come, you will know what to do when. Number three, you will have test series and assignments also, which will help you analyze your mistakes, and you will get study material, which is very useful. Plus, you have additional sessions. It's not just academics. You have lot of tips, strategies, revisions, everything which is planned in a very systematic manner. So that is what you will eventually need, unless you are so self-sufficient and self-motivated. That's a different story. It's nothing like you cannot crack without the Sigma batch. You can definitely crack just by YouTube. There are a lot of people, but there are very few such people who do that. So usually people take assistance from YouTube, they take help. It's not like only if I join offline, I can crack it. No, many students are there who are maybe in some other coaching also, in offline, online, doesn't matter. Still watch YouTube because you get full clarity over here. So the batch introduces a kind of sense of discipline, brings in that competitiveness. Is that right? Yeah. What if the voltage changes with time and it is not constant? Well, maybe sometimes you will get a spark, sometimes you will not get a conduction. So when the voltage increases, suddenly there is a surcharge of electricity, and then there is nothing when the voltage is low. So it can happen alternatively also. Is that right, Kushal? Kumar? Okay. Yes, Rama. Perfecto. Okay. Next example with Pandu. All right. Great. Last property before we go to the conductor with properties, conductor with cavities. Connecting two conductors. Connecting two conductors. Now, imagine this particular example where where you have you have a very, I would say, charged Pandu. This Pandu is highly charged. He has more charge on him. Highly charged. Highly charged. And this Pandu is barely charged. Is barely charged with any charges. Now imagine they meet each other. These two Pandus meet each other after a long time, and they shake hands. And they shake hands. What do you think will happen? What do you think will happen? Oh my God. Don't even ask. Immediately, there will be a flow of charges. Flow of charges. And why did you think that the charges will flow from highly charged to lowly charged? Actually, usually what might happen is maybe the potential is higher over here. Yes, probably this particular Pandu might be at higher potential, higher potential, higher potential, and this Pandu may be at a lower potential, lower potential. So because of this, what happens? The charges will always go from high potential to low potential, and they will keep flowing until their potentials become equal. So you might have felt this shock when you shake hands with some people. Suddenly, zoop, when shock comes. Maybe you were not charged, but your friend had accumulated some charge because his cloth or his shoes were rubbing against some material. So one Pandu was charged, and you shake hand with that Pandu, that's it, gone. The charges will come onto you from high voltage to low voltage. But it's not like if you keep shaking hands like that, the charges will keep coming. You're generating electricity. If I put a bulb on you, that bulb will start lighting. No, that will not happen. It's only for a small time till that higher potential comes down, lower potential goes up, and the potentials become same. If imagine there were two Pandus, they both were charged equally, same potential, everything, then if they shake hands, nothing will happen. Yeah, nothing will happen. And you might have seen this in the case of crows or pigeons, etc., which sit on electrical wires. Have you seen them? Yeah, seen the pigeons or the birds. Imagine this is a bird over here. This is a bird over here, like this. This bird is sitting on a wire. Why does this bird stay safe? Why is this that this bird stays safe? Because the potential over here and the potential over here is the same. So that is the reason why there is no flow of electricity. No flow of electricity. No flow of electricity. So that is why you are perfectly safe. This bird is safe. No problem at all. But by chance, if there were two wires going adjacent to each other, and this bird, very smart bird, decides I will keep one leg here and another leg over here, okay, like this bird decides that, okay, I'm going to keep one leg over here and the other leg over here. Now what do you think will happen, my dear students? Now what do you think will happen? Think about it. Yes, one leg over here, the other leg over here. Obviously it will become tandoori fry. Yeah, it will become tandoori fry. Yeah, why? Because one might be at higher potential, one might be at lower potential. Maybe this is example, this is high potential, maybe this is low potential, maybe this is low potential. So the moment this happens, you will immediately see charges will start flowing. yes, you will immediately start seeing charges will flow. Yes, there will be flow of charges. Flow of charges will be there. Yeah. So what will happen? This will definitely be in danger. Definitely be in danger. So you should never ever hold two wires of electricity like this. Same wire, nothing will happen. But please don't do that also, because by mistake, if you touch the ground, then ground is at a different voltage. So the electricity will flow through you. So don't say, sir, today told if you hold one wire, I am safe, like this bird. But you should understand the bird is in air. It's not keeping its feet somewhere else. If you hold a wire and your feet is in the ground, gone. Everything will flow through you. Okay? Be careful. Yes, dinosaur bird. Jurassic bird. Jurassic bird, this is correct. Perfect. Perfect. Amazing. All right. So, very, very important. So, coming back to the point, the charges will flow. There are two conductors like this, and you are taking a wire. Sorry, you're taking a and this is high potential. This is low potential. And you will see finally V1 will be equal to V2. So you will see that there will be a flow of charges from high voltage to low voltage till equilibrium is achieved. Here you will see it will be equilibrium, and no more flow of charges. No more flow of charges will be there. They will both have the same voltage. Okay, so this is the second aspect of it. This was the first part, and then this was the second situation. Clear, my dear students? Very, very important. Now, there is also another thing regarding this, that if you take a conductor, but you connect that conductor, to earth. This is called as earthing or grounding, earthing or grounding. Then the moment you connect that conductor, immediately the potential of that conductor will become zero, because the earthing will suck away or take or give those excess charges, and it will bring it to the potential of the earth. Earth being a massive object, it has large capacity, so it has almost negligible voltage. So if you measure the absolute voltage of earth, it is negligible. So and it is very big, it's a very weak conductor, you can say. So if you pierce a rod inside the earth, it has some minerals, it has some conducting matter in it, so it can definitely mobilize the charges. In fact, earth can be used to transmit electromagnetic waves. You will see, I mean it was there in a chapter called as communication systems. So earth has some small electromagnetic property. Yeah, so because of that, you can use that to ground anything, meaning you are basically bringing it to zero voltage. So very, very important again. So any conductor connected to the earth will come to zero voltage. And this is also the principle of, you can say, this is also the principle of 3-pin plugs. So you might have seen 3-pin plugs, meaning there is one big pin over here and the two pins over here. So maybe these two pins are connected to your appliance, whatever it could be. Maybe this is your appliance, whatever, bulb, anything, fan, motor, etc. But maybe this particular appliance is there in a box or container or maybe some casing. And imagine some Pandu accidentally touches that casing, accidentally touches that casing, and this Pandu is standing on earth, is standing on the ground, is standing on the ground. and maybe this wire inside was loose. If there is a loose wire over here, so now it is touching the casing. So what will happen is, if there are multiple cases. Number one, if Pandu, if our Pandu is wearing rubber shoes, if Pandu is wearing rubber shoes versus Pandu is not wearing rubber shoes. If Pandu is not wearing rubber shoes, what will happen? The electrons or the charges from here will go from the casing. They will go like this. They will go through the body of the Pandu and they will go inside the ground. So there will be flow of charges. There will be flow of current through Pandu's body, and this will be a very bad thing for Pandu, because ground is at lower voltage. There is some leakage of current by mistake that happened, and you happen to touch that body, maybe that fan, that bulb, or whatever. It could be a hair dryer, it could be a heater, oven, whatever. So all that current will flow through the Pandu's body. But if Pandu was wearing some shoes, then there is no path for the charges to flow. So that means there is no path. There is no path for the flow. There is no path for the flow. So that means you are basically safe. So this is good, but this definitely is not good. This should not happen. But you cannot rely on Pandu that Pandu will always wear some rubber or plastic shoes. So what we do is, okay, Pandu, don't worry. We will keep you safe irrespective of whether you wear shoes or not. What we do, we connect the casing. We connect the casing. We connect the casing, okay, which is most likely to get damaged, or the current might touch it, the wire might touch it. We take that casing and we connect it to the third pin, and the third pin, that third pin is connected by a very good conductor inside the earth, inside the earth. So it has been earthed. There is earthing done on it. So now the charges have two options. The current which comes from the leakage of that wire. So now that current has two options. Option 1, option 2. Option 1, option 2. Option 2, it can go via Pandu's body and then into the ground. Or option 1, go through this pin and go to the ground. You're like, sir, why can't it go through option 2? Isn't it good only? I mean, or it can get distributed equally. No. This path is of high resistance because Pandu is not a good conductor. Human body is not that great a conductor. So Pandu being not so good conductor, not so good conductor, not so good conductor, this path is of a high resistance. So high resistance path, high resistance path. So this path made of conductor, this is very, very low resistance. This is very, very low resistance path. So all of the charges will flow from here. So, there will be definitely flow of current through the path 1, flow of current via path 1. Pandu, nothing will happen. Pandu, nothing will happen. So our Pandu will be basically safe. Our Pandu will be basically safe. Is this absolutely clear? This is the concept of earthing, guys. Clear, everyone? After this, I don't think you will have any other doubt regarding earthing, connecting of conductors, and so much more, right? So I have done most of the properties. We will see some questions on this, but before that, okay, fine. Just probably take this question here. Actually, not needed. Okay, anyways, let's do the first question. In a metallic conductor, under the effect of applied electric field, the free electrons of the conductor. So you have a metallic conductor, just visualize this. You have a metallic conductor like this, and under the effect of applied electric field, the free electrons of the conductor will move in straight line paths in the same direction, move with uniform velocity, lower to high, drift from high potential to lower potential, move in curved paths from lower potential to higher potential. So we are talking about electrons over here. So in a metallic conductor under the effect of applied electric field, what will happen when the moment you apply some kind of electric field, the moment you apply some kind of electric field over here, maybe that electric field will go like this, yeah, maybe like this, like this. Electric field is there. Maybe then I can say electric field always goes from high potential, high potential to low potential, to low potential. So on the electrons, on the electrons which are negative charges, on the electrons which are negative charges, the force on it, the force on it will be exactly opposite to the field. The force on it will be exactly opposite to that of the field. So it will definitely go from low potential to high potential, low to high, not high to low, low to high. So C option is out. Move in straight lines in the same direction, not necessarily. So they might take curved paths also, because I don't know how the field lines are. They might take curved paths, etc. So they might take some paths like this, but they will definitely go from low potential to high potential. So they move in paths which are not necessarily straight, but they will 100% go from low potential to high potential. Electrons, those are negative charges. But net flow of charge, think about it, is happening from higher to low. So the net positive flow will always happen from high voltage to low voltage. But depending on the sign of the charges, the negative charge will always go from low to high. So I think the answer will be D. Perfect. Yes. Is that clear, everybody, with me on this? Understood? Let's move to the next question on your screen. Two spheres are there, R1 and R2 are the radii. They are connected by a wire and they are given some certain charge. The charge will be greater on which one? Okay, so let's draw those two conductors first. One is like this, one is like this. R2 is more than R1. Okay, let's say this is R2. Let's say this is R1. And now they are connected by a wire like this. You are connecting it by a wire. So what will happen is the charges will get distributed and they will come to equilibrium. When you connect it, it will be in equilibrium. And in equilibrium, what will happen? The voltage of the bigger sphere will be the voltage of the smaller sphere. Potential of a sphere, what's the formula, guys? Or any charged body, it will be kq by r, isn't it? K is Coulomb constant. Here you have q1 divided by r1. Here you will have k charge 2 by r2. Remember the formula for potential, kq by r, right? K cancels. So from this we get q1 by q2. q1 by q2 is r1 by r2. But r2 is more than r1. So denominator is more, numerator is less. So 100% this is less than 1. So q1 will be less than q2. So q1 will be definitely less than q2. So on the smaller one, the charges are less. On the bigger one, the charges are more. Hence, on the charge will be more on surface A. The charge will be more on surface A being the bigger one. So this was our A sphere. This was our B sphere. B will have less and A will have more. A will have more. Is this clear, everyone? Very simple. So most of the times you will have to use kq by r formula. Kq by r is the electric potential. Look at this question. Two spheres of some radii are given some charges, and if they are connected by a wire, the final charge on the smaller sphere is. Okay, just like the previous one, again you have a big one, you have a small one, and you are now connecting it with some wire. Radii are 1 centimeter and 2 centimeter. Let me put it over here. This is, let's say, 1 centimeter. This is 2 centimeter. Charges are also given. 1 centimeter is given 10 to the power minus 2 coulomb. This is given 5 into 10 to the power minus 2 coulomb. So, initially, if you ask me what is the total charge, initially, if you ask me what is the total charge on it, yeah, if you ask me what is the total charge. total charge of the system. Total charge of the system. It will be 5 plus 1 into 10 to the power minus 2, which is 6 into 10 to the power minus 2 coulomb. Why am I calculating the total charge? Because I know eventually what will happen is the charges will get distributed, maybe Q1 over here, Q2 over here, but Q1 plus Q2 will still be 6 into 10 to the power minus 2 coulomb. This is simply because of charge conservation, which we have learned. Charge conservation principle. The total charge of the system should be conserved. Oh, perfect, sir. What is Q1, sir? What is Q2, sir? I don't know. No worries. I just know one more thing, that this guy's potential and this guy's potential will be equal, right? So the potential of the big guy will be equal to the potential of the small guy. And what is the formula for potential? K, Q by R, and here also K, Q by R. Okay, perfect. So what can we do? K will get cancelled. So therefore, start substituting the charge originally, sorry, not charge originally, whatever is Q1 and Q2, I'll just put it as it is. So Q1 by R1, what is R1? It is 2 centimeter. So 2 into 10 to the power minus 2 meters. Q2 is, I don't know. R2 is nothing but 1 centimeter. Okay, minus 2 power of 10 will cancel on both sides. So therefore, from this, I am getting Q1 by 2 is Q2. Therefore, Q1 is 2 times of Q2. Q1 is 2 times of Q2. Now use this relationship. Now, what will you get? The relationship 6 into 10 to the power minus 2 coulomb is Q1. Q1 is 2 times of Q2 plus Q2 plus Q2, which is basically 3 times of Q2. That is 6 into 10 to the power negative 2. Therefore, how much will be the value of Q2? 6 by 3, which is 2. So 2 into 10 to the power minus 2 coulomb. So if Q2 is 2 into 10 to the power negative 2 coulomb, hence, what can you tell me about Q1? Therefore, Q1, how much will it be? Q1 is 2 times of Q2. So 2 times of 10 to the power minus 2, which is 4 into 10 to the power minus 2 coulomb. Anyways, if you add 4 and 2, you shall get 6, which is exactly what we expect. So the charge on the smaller sphere has a charge of Q2. Q2 will be 2 into 10 to the power negative 2 coulombs. So answer D is the right answer. If the question was smaller sphere, the answer would be 4 into 10 to the power negative 2 coulomb. This is how you solve the questions. Is that clear, everyone? How to solve? Modern physics, lot of time is there, man. Yeah. Chargers is a good example. Chargers usually have 2 pins, they don't have 3 pins. That's what you will see. Okay. Now, the next type of thing, which is conductors with cavity. Conductors coming up with cavity. What happens in that case? Now, there are multiple scenarios over here. Observe this carefully, guys. Observe this carefully. If at all, you see that there is a conductor. If you see that there is a conductor like this, and there is no charge inside, there is no charge which is there inside, then you will just see that the charges on the conductor will be only on the outer surface. The charges, if at all, on the conductor, the charges will be on outer surface only. Outer surface only. This is when there is no charge inside. Versus, imagine a scenario where you have a conductor, like this. All right. Wait 1 second. I'll draw a big one because I need some space. Where you have a conductor with some cavity inside, But this time, imagine there is some charge over here. Extra charge is there inside the cavity. The moment you have a charge in the cavity, everything changes. You will see that charge will start pulling, the electrons or pushing the electrons depending on its sign. Because it's positive, you will see negative charges will start accumulating here. Because this charge is closer to this surface, more electrons will be here. This charge is farther from this surface, so less electrons will be here. If this was negative, this will be positive. If this is positive, this will be negative. These charges are just traveling from outer surface to here. These are now our induced charges, guys. Yes, they basically go from outside to inside like this. They're just coming like this. The electrons will travel from outside to inside like this. These are basically induced charges. And because they are traveling from one place to another, wherever they leave, they will create a vacancy and there will be an equal amount of positive charge. There will be an equal amount of positive charge on the other side or opposite charge. So if this was negative, this will be positive and this will be negative. Just that's it. I mean, the signs will be opposite, that's all. Is this clear? So these are all induced charges and both inside and the outside. Just because there is a charge inside the cavity. Just because there is a charge inside the cavity. What if the charge was outside the cavity? Then also, maybe outside the conductor itself. What if there is a charge over here? What if there is a charge outside the conductor? Then you will notice this positive charge will start attracting the electrons like this, and these electrons would have left their individual atoms, creating an equal amount of positive charge on the other side. These are also again induced charges on the surface, induced charges on the surface. But in spite of that, you will not see any charge on the inner surface. So there will be no charge on the cavity, surface. Yes, there will be no charge on the cavity surface. All the charges are just getting redistributed on the outer surface. This positive will pull the electrons. If this was negative, it will push the electrons away and these positives will be here. But nothing will affect inside. Okay, there is no reason for it to get affected. This is the situation. These are the three only possible situations for cavities. There is no charge, there is charge, but inside versus outside. That's it. These are the only three possibilities. Now, if you ask me how will the electric field lines look like, that is the most interesting thing. Let's have a look at it. Say for example, if you oh my god, 1 second. Or like this. Okay, this is a conductor. This is another conductor like this. Okay. This is just to give an example of how the charge distribution works. So these are examples of two conductors, and imagine we just happen to take some kind of a negative charge inside the cavity. Let's say there is a negative charge which is placed deliberately inside over here. Because the negative charge is not placed symmetrically, it is slightly more towards the left hand side. So it will ask all, or it will pull the positive charges more over here. So we'll start seeing the positive charges getting accumulated on this side. So more positives will be here, more positives will be here. And as you go away, the positivity will decrease very few positive charges will be there on the other side. Okay. So now, if you ask me how will the electric field lines look like? Well, look at it. It will start from positive and should go to negative. So it will be like this. It will be like this. It will start getting curved. And notice one interesting aspect. No matter where the electric field is coming from, it is always being perpendicular to the surface because it's a conductor. At the end of the day, it is a surface. So it has to be perpendicular to the surface of the conductor. Everywhere it is perpendicular. Yeah. So it is curved and it is terminating on the negative charge. If the inside charge, is, let's say, negative Q, the total charge, the charge on the charge, induced charge, the induced charge on inner surface, on the inner surface is going to be exactly positive Q. It's exactly going to be opposite in nature. If this is minus 5 coulomb, this will be totally the total induced charge. The total induced charge will be exactly plus 5 coulomb. This is minus 6, this will be plus 6. Is that clear? Exactly opposite. And there is a reason for that. If suppose somebody decided to take a Gaussian surface over here, everywhere the field will be 0. If you take a Gaussian surface, in the solid part of the conductor, the field will be 0. So the flux will be 0. That means the total charge inside should be 0. So as much negative, that much positive charge should be there. So this comes only because of Gauss law. How many of you got it? Give me a thumbs up. Why this charge is not more or less? Exactly same magnitude but opposite sign. If you take a Gaussian surface in the solid part of the conductor, what is happening? Everywhere in that solid part, field is 0. Why field is 0? I have explained before by proof by contradiction. So, if field is 0, flux is 0. So, in the Gauss law, if flux is 0, charge totally inside is 0, inside this Gaussian surface. So, if there is negative, an equal amount of positive charge should be there. Is this clear? Very good, Prajit. Awesome, Rama. Now, by conservation of charge, there must be an equal but opposite charge on the outer surface. So, you will see probably negative charges like this. So, 1, 2, 3, 4, 5, 6, 7, 8. So, we'll have to draw 8 charges exactly. 1, 2, 3, 4, 5, 6, 7, and 8. So, total induced charge on outer surface will be exactly negative Q, but this is because of conservation of charge. By conservation of charge, very, very important. But there is one very interesting thing which is happening. Do you see the negative charges are distributed uniformly, unlike the positive charges? You'll be like, why, sir? How is it that the negative charges decided to distribute uniformly? I thought there will be more negative here and there will be less negative here. Do not forget the fact that there is no electric field line between the positive and the negative or between the inner and the outer surface. Rather, the conductor acts like a shield, acts like a barrier, acts like a wall which hides the information of whatever is happening inside, because electric field will have to terminate on the surface of the conductor. So, if the electric field terminates, and electric field was like an information to the outside world, it tells you the aura, it tells you what is happening. That's it. The outside charges have no way to know what is happening inside. So, when they don't know anything, they will be like, oh, the surface is uniform. So, I have no reason to be on this side or this side more. So, they will not be partial or biased. So, they will uniformly get distributed because there is no communication link. There is no field line which is going through the conducting surface. So, that's the reason why when you go outside, very interesting, the field lines are uniformly distributed radially like this from all the sides. It's a radial field which comes. It's not more on one side and less on the other side. Is this clear? This is the most interesting field diagram that you can think of. Did you love this concept, guys? Charges are too small but not visible, is it? Oh my god. What to do? What to do? Okay, I've drawn it. Now I cannot erase it because a lot of things will go, and I think um, maybe I can draw it like this. All the positive charges I have shown. Okay, I will use a thicker pen. Sorry, guys. Negative, 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 negative. Okay, now is it clear? Everybody with me? This concept is now like a shield. What does a shield do? It protects you from the outside. Like you put UV cream, it protects you from the UV rays. Same way, the conductor acted like a shield for a person standing outside. Imagine this negative charge was here or here or here. These field lines outside would never change. The charge distribution, the negative charge distribution outside would never change. So if there is a Pandu standing outside, there is no way the Pandu can even tell that there is a charge inside, because the conductor could be independently charged negatively and he won't even see the cavity. He won't even know that there is something inside. And even if this charge moved here and there, nothing will get affected because field lines are not going through. Nothing is going through. Lack of information. So it has acted like a shield. So this can be used for some specific purposes. Like for example, you want to go out of the coverage area of your mobile phone, and mobile phone transmits signals using electromagnetic fields, electric field. So you place your mobile inside a metallic conductor. So that's it. The electric field lines will break, they will stop, they will terminate on the inner surface, and they will abruptly start over here. But understand, once there is a break, gone. So there is no way, you know, you can know where the mobile phone is, and the signals will start getting interrupted, and you will see a complete lack of information to the outside world. So that's how electrostatic shielding works. Yeah, it also works the other way around. When the charges are coming from outside, I'll just show it to you. So this is also called as a Faraday's cage. You can see this person is standing inside a net of conductor. This is like a conducting body, and even if a lightning strikes that person, that lightning will not go through the person. It will first hit the conductor, it will go around him, but not through him. That is the reason why you are very safe in a car when a lightning strikes. You might think, sir, lightning will strike, the car will get damaged, and I will also burn. No, the charges will flow through the body of the conductor and it will go through the ground. You are safe, nothing will happen. So this is the concept of electrostatic shielding. Imagine the charge being outside. Okay, just imagine a similar charge being outside right over here. Okay, imagine a charge over here like this. Now what will happen? It will start asking the positive charges, hey, come near me. So there will be a lot of positive charges around him like this. And very soon the positive charges will disappear, and these positive have come because they have uh, they are like vacancies. The negative charges have gone away from them, so probably you will see something like this, some negative charges over here. So the negative charges will go that side, positive charges will come here. So you will see a polarized conductor. You are going to see a polarized conductor, polarized conductor. And you will see also induced charges on the surface of the conductor. If you ask me how will the electric field lines look like, well, from the positive to negative, like this, like this, like this, like this, maybe also like this, like this, maybe like this, same thing over here, always have to be perpendicular though, no matter where. Yeah, always have to come perpendicular. Like this. And, oh, sorry, I showed all the positive charges over here. I'm so sorry. These were negative charges, guys. So sorry. My bad. Something ran in my head. These were the negative charges. Sorry. Why did I show positive? My bad. Okay. And you will start seeing the electric field lines here too. And maybe this is going to be like this. Something like that. This is how the electric field lines will look like. Okay. For a charge which is outside, inside everywhere, the electric field will be 0. Here, electric field will be 0. Here, electric field is 0. Everywhere, electric field is 0. So, inside world has no clue what is happening outside. Again, you have shielded yourself from the outside world. Okay, you have shielded yourself from the outside world. Most important thing again over here, everywhere, field lines are going to be perpendicular every single place, even here, guys. Everywhere the fields have to be perpendicular to the conducting surface. Cool. So that is the concept of electrostatic shielding. Okay, and which I have just explained it to you. Actually, this was only electrostatic shielding. We don't need this slide. Okay, perfect. So let's solve some questions based on this. In the following two statements, what do you think is right, wrong? The outer body of an aircraft is made of metal which protects persons sitting inside from lightning strikes. Okay, the electric field inside the cavity enclosed by a conductor is 0. Yes, we just discussed this. Electrostatic shielding, I believe. Yeah. Simple. Both A and R are correct, but R is not the correct explanation. Electric field inside the cavity enclosed by a conductor is 0. The outer body is made of metal which protects the person sitting inside from lightning strikes. Well, the thing is, actually, if you see over here, see, yes, the metallic body is definitely going to protect that person who is sitting inside, because the charges will not flow into the person. It will just flow through the conducting body from outside. Yes, the electric field inside the cavity is also 0, but not the real correct explanation. The real correct explanation should be, even if the lightning strikes, then the charges will flow through the conducting body, and yes, no field will be there inside, and all the charges will flow inside the ground. So that would be the right explanation for why the person is protected. Why the person is protected. So the person protection reasoning is not given. That is the reason why C option. Is that okay? Otherwise, both statements have perfect meaning, right? Okay. Now, coming to some questions on more on, your, what do you say? Finding out the charges. Yeah. Just take this particular example where, imagine you have a conductor like this. Okay. Then we take another example where you have a conductor and a conductor like this. And okay, maybe one more example over here like this. Okay. Now imagine I tell you that there is a charge on the shell. The total charge on the shell is basically Q. And I want to figure out, how is this charge exactly there? Where and all is it there? Well, this is a conductor with a cavity inside. And I just told you, if there is a conductor with cavity, what exactly happens? Well, if there is a conductor with cavity and if there is no charge inside the cavity, all the charges will stay on the outer periphery. Nothing should stay inside. The charges are only there inside if there is a charge inside the cavity, like in this case. In any other case, there is no charge on the inner surface of the cavity. So that means if you go by that logic, there is no charge inside over here. So whatever charge will be there will be only on the outer surface. So which means it will look something like this. Observe it carefully. So all the charges will be there over here on the outer surface. All the charges will be there on the outer surface, and it will be basically plus Q. There will be no charge. There will be no charge over here. No charge on the inner surface of the shell. All the charges are on the outer surface. Okay, perfect. Sir, what if I put a charge over here and let's say it is plus Q, plus Q. Now tell me what will happen. Now if you put a plus Q charge, immediately there will be a negative charge which will be developed like this. There will be a negative charge which will be developed, and this will be negative Q on the inner surface, of course, and an equal amount of charge, on the outer surface, a plus Q on the outer surface. This is just like this particular question. Where you had a charge inside, it creates induced charge and again induced charge. Just the difference is now the charge is placed symmetrically, so all the charge distribution will also be symmetrical. So a negative equal amount of charge, and by conservation of charge, you will see a plus Q on the outer surface. Is that clear, my dear warriors? All right, very good. Now, next thing, let us just say that the inner shell has a charge of Q, and the outer shell is, let's say, given to be neutral. Now, how will the charge distribution look like? If you look at the inner shell, the inner part of the inner shell has no charge, so there is no reason for any charge to be over here. So there will be no charge on the inner shell's inner surface. So whatever charge is there will be there on the outer surface of the inner shell. Okay, so that will be basically plus Q. Exactly opposite surface will have exact negative charge always. Negative of it. If this is negative Q, this will be plus Q. If this is positive Q, this will be minus Q. So an exact amount of negative charge on the exact opposite surface. That's what you will see. Okay. On the inner surface of the outer shell. This is on the inner surface of the outer shell. But by charge conservation, since the outer shell is neutral, you should see an exact amount of positive charge on the outer surface of the outer shell. So this will be plus Q. So this is how the charge distribution will look like. Is this clear? Very good. Excellent. Sir, but what if it is given to me that, sir, the inner shell has a charge of 2Q, sir, and the outer shell, sir, it has a charge of, let's say, some 5Q. Okay, or inner shell has Q and outer shell has 5Q. Sir, what in that case? Well, simple. See, first of all, innermost region has no charge. So this inner shell's inner surface will anyways have no charge on it. If there was a charge, then it will develop an equal and opposite charge. So all that charge Q should be there on the outer surface, of the inner shell. The moment you have this, the exact opposite side should have an equal amount of negative charge. Now, the outer shell together totally had 5Q charge. So if it has negative Q, what should be there on the outer side so that the total is plus 5Q? Now it is very obvious that it should be plus 6Q, so that you can clearly see over here that total, that total will be basically 5Q. Charge has to be conserved. So there will be a charge of basically 6Q. There will be a charge of 6Q on the outermost surface. On the outermost surface. Is this clear? How to find the charge distribution? At the end of the day, it is nothing but conservation of charge, and opposite surfaces should have same but opposite sign. Same but opposite sign. Okay? Is that clear? Very good. Amazing. Sir, but what if instead of you had, instead of shells, you had plates? For plates also it is very similar, guys. I'll tell you what it is. For plates also it is very similar. For plates also it is very similar. Imagine you had a plate like this, or a sheet like this. Then you had two plates. Oops. Then you had two plates in front of you like this. Then you can also take three plates for that matter. So if you have a single plate and you have been told that the total charge on the plate is, let's say, Q. If the total charge on the plate is Q, then without even telling, you should be like, okay, this is a large plate, the charge will get distributed equally. So this side, so this right side will develop some kind of charge, maybe like this. The left side will also develop the same amount of charge, let's say like this. This will be Q by 2. This will be also Q by 2. But please remember, in the inner region, there will be no field. Here, the electric field will be 0. The electric field will be present only outside. So here there will be electric field. Here there will be electric field. Yes, here and here electric field will be there. But in the inner part, that solid part, no electric field will be there. Okay, because it's a solid part of a conductor. So the charges will get distributed equally. That is for a single plate, which is very simple. But sir, what if the situation is like this? What if the situation is something like this, where, for example, the total charge over here, the total charge on this plate, example is Q, and let's say this is completely neutral. Okay, or let's say another question where this has a charge of Q, and let's say this has a charge of, let's say, for example, 3Q, or let's say this has a charge of Q and this has minus 2Q. Okay, so what to do in these situations, or maybe minus chumma, some random example, minus 5Q. Okay, you can take anything. What to do in such situations? First, always check what is the total charge. In such situations, always check what is the total charge on both the plates. Now, the total charge on both the plates is Q plus 0, which is basically Q. Now, take that charge, total charge, and divide it into two equal parts. So, it will be Q by 2 and Q by 2. So, now what you do, once you get Q by 2 and Q by 2, exactly put Q by 2 and Q by 2 on the outermost surfaces. So, here and here. Here you will have Q by 2. Here also you will have Q by 2. But that's not the end story. The total charge has to be Q. So to conserve the charge, in the next step, well, the inner surface over here should have Q by 2, so that you can clearly see now that this total will be Q. This total will be Q, which is what you expect. This is neutral. So 100% there will be a negative charge of minus Q by 2, which you can see that their total will be 0. their total will be 0. Conservation of charge. It's that easy, guys. Okay? Take the total charge, divide by 2 and put it on the outermost surface, then use charge conservation or whatever. Say for example, we take this Q and 3Q. First count, first you start off by counting what is your total charge. What is your total charge? Your total charge will be Q plus 3Q, which is basically 4Q. Divide that into two parts. One is 2Q, another is also 2Q. Equal always. So here you will have 2Q charge plus here also plus 2Q charge on the outermost surface. Now conserve the charges. That's it. Now just have to conserve the charges. The total charge here is Q. So that means there must be some kind of negative charge over here. And total here should be 3Q. So this should be basically plus Q. As you can easily see that their total is coming out to be 3Q. And here 2 minus 1 is 1. So their total is just coming out to be Q. This is how you solve these questions. We can do it for 3 charges, 4 charges, anything. So even this you can do now. It's very simple. Or let's say we have 3 plates. Okay. Maybe this had Q charge, this had minus 2Q charge. And let's say this had, some 3Q charge. Now what will you do? Now what will you do? Again, find out the total, guys. Just find out the total charge. The total charge will be Q minus 2Q plus 3Q. This is minus Q plus 3Q, which is plus 2Q. Divide it into two parts. It will be Q and Q. So the moment you divide it into two parts, which is Q and Q, put it on the outermost surface here and here. So this will be also plus Q. Now start using charge conservation. That's all. If this is plus Q, it's obvious that over here already Q charge has been taken care of. So there will be no charge on this side. So 100%, this part will have no charge. So this will be 0. No charge at all. No charge over here. Same thing do over here, plus Q. This is 3Q. So on the inner side, this should be plus 2Q, so that you can see their total should be 3Q. Here, as you can see, the total is just Q. Now what about over here? Opposite surfaces should always have equal charges but of opposite sign, just like for shells. Just like we did it for shells. Opposite surfaces equal but opposite in sign. Equal but opposite in sign. Same thing over here also, guys. Okay, just do that. Same thing. You will see that if this is 0, this will be also 0. No doubt about it. This is also going to be 0. And this will be exactly opposite in sign. So this will be minus charge over here. This will be minus 2Q. So this is 0 and this is negative 2Q. If you add the total is again coming out to be negative 2Q, conservation of charge. So this is how you solve plate questions or shell questions. Okay. All right. I'm so glad, Vasuki. Yep. Awesome. I'm so glad, Vasuki. Very good. Okay. Now that we have learned this, let's also talk about dielectrics and polarization. This is the last few things, and then I'll give you the formulas. See, imagine you have a medium, you have air, water, glass, wood, anything, and from outside you have some kind of electric field which is entering it. This is basically your external E naught is basically your external field. Then the moment the external field passes through glass or air or water, some liquid, some gas, some solid, this is some medium, you will see that it gets affected and there is something like polarization which occurs, which I have explained you during induction and methods of charging. So because of it, some polarization happens within the atoms, or if the atoms or molecules themselves are polar in nature, so they will start shifting their electron clouds. Because of the polarization effect, you will see this polarization starts creating its own its own electric field, but in the opposite direction. Yes, but in the opposite direction. This is called as induced field. This induced field is due to the polarization effect, due to the polarization effect of that particular medium, solid, liquid, or gas, because of which you are opposing the external field. There will be only some remaining field inside. So maybe it is not as strong as before. So this is what is remaining. This is your net electric field, which is your resultant field inside the medium, inside the medium, inside the medium. This is the resultant field inside the medium, which is definitely less than our external, less than our external field. This is basically now called, this medium is now called as a dielectric medium. Okay, so it comes because of the dipoles which are formed because of polarization. That is why it is called dielectric medium. So this medium is now said to be dielectric. So it is basically non-conducting in nature. It is non-conducting in nature, but it weakens the field. It weakens the field. It weakens the field which is there inside. So that is called as a dielectric medium. Now, the moment you have a dielectric medium, here is what I can say. This is induced, this is external. Okay, observe this carefully. Yes, the net electric field will be our external field E naught minus our E induced, and obviously E net is going to be less than E naught because you are subtracting something from it. The factor by which it reduces. So if I have to write, our net electric field is equal to some external electric field divided by some number. This is not Coulomb constant. This is called as the dielectric constant of the medium. Dielectric constant of the medium. This tells me the factor by which, the field intensity, the strength reduces inside that medium, like glass, wood, rubber, whatever it is. So very, very important formula. Now, from this particular formula, you can get a lot of other formulas as well. Like for example, let me show you. Say, if you continue with that formula, which is E is equal to your E naught divided by K. Now we can find out how much is E induced. From here. E induced is E naught minus E net. Now our E induced is nothing but our E naught minus our net electric field. E induced is E naught minus the net electric field. How much is the net electric field? It is E naught by K. So I'll just put it over here. So E naught is there minus, again E naught is there, divided by K. So how did I get it? Just substituted E as E naught by K. Taking E naught common, Therefore, I will get the induced electric field is equal to E naught is common, and then the whole thing into 1 minus 1 by K. Now, this is also a very important formula. Sometimes they can directly ask you a question, what is the induced electric field? What is the induced electric field? It is external field into 1 minus 1 by dielectric constant. Now, if you ask me this dielectric constant, it depends on the medium. Like for example, for air, K for air roughly is almost 1. K for wood, etc. Is typically in the range of 4 to 5 units. I don't know the exact values, but I'm just telling you. Dielectric constant for ceramics is in the typical order of 200 to 400 units. Actually, no units over there. It's a constant without units and dimensions. It's just a pure number. It's a ratio. So dielectric constant for ceramics is in the range of, typically in the range of 200 to 400. For air, it is 1. If you ask me, what is the dielectric constant for metals, which are basically conductors? Metals for basically which are conductors. Any guesses, guys? It will be nothing but infinity. And there is a very simple reason for it. If K becomes infinitely large, the field inside will become 0. The field inside will become 0, which is the case of conductors. So for metals, it is infinity. For ceramic like objects, it's 300, paper, wood, typically 4, 5, 10 like that. And for air, vacuum, it is 1. Okay, very, very important. Yes, today's lecture is 12th grade lecture. Correct. Now, also from this, since you are seeing that electric field, the net electric field is E naught by K, since you are seeing that our net electric field is nothing but original electric field divided by K. If it was a point charge, just imagine if it was a point charge and you were trying to calculate at this point how much electric field is there, but maybe you place that point itself in some medium, so because of which the field over there will be something else. The field over there will be something else. It will be a slightly weaker field, because you placed it inside some medium. Okay, you have placed it inside some medium. Okay, so start substituting the values and see what do you get. Usually our E naught value is 1 by 4 pi epsilon naught charge divided by the distance. And needless to say, you have to now divide it by K. Okay, interesting. Observe one interesting thing now. Okay, observe one interesting thing. Okay, I'll just put 1 by 4 pi over here, epsilon naught over here, Q by R as it is, and this K, I'll put it with K. I'll put it with K. Observe now what is happening. Deliberately I have put K with epsilon naught because now I can replace it with a new thing and I will call it 1 by 4 pi. Okay, 4 pi. You have Q, you have R also. Okay, you have R also. This epsilon naught K, I will call it epsilon of the medium. This is now called the permittivity of the medium. Permittivity of the medium. Permittivity of the medium. So permittivity of any medium is permittivity of free space, whose value is 8.85 10 to the power minus 12. Okay, the whole thing multiplied by the dielectric constant, multiplied by the dielectric constant. It is not Coulomb constant, it is dielectric constant. This you can use it for calculation of force, for calculation of field, anything. Very, very interesting. The field now is not 1 by 4 pi epsilon naught, it is 1 by 4 pi epsilon m Q by R. So very interesting looking formula. Okay, everybody till this point absolutely clear how this concept of dielectric works? Okay, I'm so glad, Roshish. Let's do some questions and I'll quickly give you some question formulas. Okay, imagine this. 2 point charges have some distance between them and there is 8 Newton force. How much force will be there between them if it is in water at the same distance? So imagine there are two charges and there is some kind of force between them, and that force is basically 8 Newton. Now you take those same charges, same distance, but now it is in some medium, some water or something is there. So the moment you place it in the water whose dielectric constant is given to be, let's say, 80, this force will no longer be 8 Newton. This will be some new force, and this force, just like our field calculation. Look over here. Where did it go? Yeah. The field reduced by K factor. Same thing, you can do it over here. This force will also be the old force divided by the dielectric constant. So old force is A, dielectric constant is 80. So it will be 1 by 10, which is 0.1 Newton or 1 by 10 Newton. So that is the new force, 1 by 10th of a Newton. Is this clear, my dear students? How the force reduced? Yeah, this is purely because there were dipoles which were formed inside and they started opposing the external field and polarization effect occurred, and because of which the field strength reduced. So the new field is original field by K, K being the constant of the medium. You can also figure out how much induced field was there, etc. So in the same question, for example, induced force was asked. How much force is induced? If this was asked, then I will think like this. The net force will be the old force minus the induced force. Net force is 0.1, old force is 8, induced force I do not know. So from this, the induced force is 8 minus 0.1, which is 7.9 Newton. So the induced force is 7.9 Newton. So the force reduced because there was another force of 7.9 Newton which was applied by the medium. Please understand the induced force is by the medium. These questions can also be asked. How much force is being applied by the medium? Answer will be this. How much force will be applied by the medium? Then you will calculate this. Okay, so the resultant force remaining is just very small, 0.1 Newton. The liquid has reduced the force drastically from 8 Newton to 0.1 Newton. Okay. Now, the last couple of things, just to give you over here. If you have a sheet like this, if you have a sheet like this, I think I gave you this last lecture, but just giving it to you once more, over here. The field will be sigma by epsilon naught 2 times, and our sigma over here is going to be, if this is the charge and there is some area, it will be the charge by that area, charge per unit area of that sheet. So there is a charge sheet over here. So this will give me how much is the field which is there on both the sides. Okay. Since this field is uniform in nature, then I can clearly say that dV by dr is also going to be constant. Therefore, delta V by delta R will also be a constant, or rather, if dV by dr is constant, I can see that the voltage will be directly proportional to that distance. Okay, I can take voltage directly proportional to the distance. So if you show equipotential lines, the equipotential lines will go like this. Equipotential lines will go like this. And as you move away, the potential will keep on decreasing linearly. So the potential changes linearly. The potential changes linearly. Very, very important. The potential will change linearly. And if at all you want to find the potential difference, it is, I can say the potential difference will be, directly proportional to the distance. So it will be some constant multiplied by delta r. That is also something which you can say. Okay, that's not a big deal. It is just linearly proportional to the distance. Okay, very, very important thing. Next important thing is for the shells and the spheres. Okay, for the shells and the spheres. So if you have a hollow sphere, like this, imagine a hollow sphere, or even if you have a solid sphere, but which is conducting in nature. Very, very important. This is a conducting solid sphere or a hollow, or basically a shell, you can say. Irrespective of that, the charges will be only on the surface of a conductor. The charges are only on the surface of a conductor. Keep that in mind. So both a sphere and a shell have the same formula, same distribution, only because the charges are only on the surface. Yes. So the charges on the surface only. Charges are on the surface. So if you try to find what is the electric field inside, the answer will be 0. Everywhere inside the field will be 0. The electric field outside simply will be nothing but 1 by 4 pi epsilon naught, the charge divided by the distance. So this is when you are inside, this is when you are outside. So this is when you are less than r, this is when you are more than r. This is for the field. Same thing applies for potential also. So if you are outside, the potential formula is just 1 by 4 pi epsilon naught q divided by r. Sorry, this was r square, guys. So sorry, this was field. For potential, it is r. And this is when you are outside. That means r is more than your radius of the shell. But the moment you are inside, be careful. Everywhere, lot of people make this mistake. The moment you are inside the shell, lot of people make this mistake and they say that it is 0. Wrong. It will be constant. It will be the same everywhere, same as that on the surface. How much will it be on the surface? Kq by r. So this will be 1 by 4 pi epsilon naught q by this r. This r, the radius of the sphere. This is the crux of this formula. Very, very important, guys. Okay, very, very important. If you ask me the graph part of it, if you ask me the graph of it for the field, then for the potential, how will it look like? Let me show it for you. This is distance, this is potential, this is field. It is 0, then suddenly jumps and becomes inversely proportional to r square. So it will be 0, then it will jump and inversely proportional to r square. Okay, the abrupt change happens at the surface. Same thing over here. It will be constant. It will be a constant till here, and then it will become like this. It will be inversely proportional to r. Inversely proportional to r. So this is the graph for potential. The abrupt change will happen, at the surface. These are the graphs and the formulas. Keep these in mind. Next thing is for the solid sphere. Now, when it is a solid sphere, it is understood it is a non-conducting nature. Solid sphere which is uniformly charged. Non-conducting, uniformly charged. Because if it was a conductor, how can you keep the charges inside? They will always go outside. Uniformly charged. In such cases, be careful. When you are inside, the field is versus outside. When you are inside, I had given you the formula 1 by 4 pi epsilon naught last time. Q divided by R cube and multiplied by R. This is capital R cube, that radius of the shell. So this is when you are inside, guys. That means R is less than R. But the moment R is more than your sphere radius, it just behaves like a point charge. So 1 by 4 pi epsilon naught Q divided by R square. So this is for the field. Outside it behaves like a simple point charge, but inside it is linearly proportional to R. So if one were to draw the graph of this, the field, it will look like this. It will look like a straight line till here, and then it will start falling down like this. Here it is proportional to R, here it is inversely proportional to R square. The abrupt change happening on the surface. Okay, this is the graph of field versus the distance for a non-conducting uniformly charged sphere. How about potential? Inside versus outside. When you're outside, it's just like a point charge. So 1 by 4 pi epsilon naught Q divided by R. So this is basically when you are outside. So if you again draw a graph over here, this is versus distance. This is for potential. When you're outside, it is very easy. It is just going to be inversely proportional to R, just like your point charge. The problem happens when you're inside. So 1 by 4 pi epsilon naught. Here you put Q, then you put 3, or rather you put 3. Okay, forget that. Just put Q over here. And now you put over here 2 times R cube. This R, the radius of the sphere, 2R cube. And on the top, you put 3R square. 2, 3, 3, 2. That's it. That's one major difference. This is R cube, this is R square. Higher power will be there below because eventually dimension of length should come below. And that's it. Over here, you will put minus R square. So this is a quadratic equation. So you will see it's a quadratic equation. So, it will be a parabola. This part will be a parabola. This part is basically a parabola. After that, it is a rectangular hyperbola, but the first part is a parabola. So this is the weird equation when you are inside a uniformly charged solid sphere. For hollow sphere, it is very simple. Inside everything is zero except for potential being constant. Outside it behaves like a point charge. But the moment you have a solid sphere, this is how it behaves. Okay. So these were the formulas for fields and potentials, guys, which you should know. The graphs also you should know. Direct formula based questions can come. Okay, find the field here, find the potential here, what is the potential difference here, how much is the field as compared to the surface. Simple ratio based, calculation based questions can come over here. Okay, but as we see advanced questions, you will see some complex questions as well. But till now, if you are understood, okay, these formulas, more than enough. Okay, so I've kept some homework question for you. Like these questions were asked in the JEE exam. How is the graph going to look like? Okay, what's the potential inside a sphere? So you can just solve these questions as homework. I can just show it to you, this one question as homework, and this particular question also directly based on this as homework. Okay, that's it for today. And if you want more such classes, please join the Sigma batch. It's on offer. The batch has all the features that you need, and the link for joining the batch is there in the description box. And yes, the entry point will close after this, right? So you want to take the full price benefit, make sure you join it as soon as possible. If you've forgotten to like, smash the like button. If you have not yet joined the channel, subscribe. And yes, if you've done both, make sure you solve the homework question and put the answers in the comments. The PDF will be shared to you very soon. Bye bye. Take care.